Alright, time for another DraftPhysics.com video presentation. A response video to two different videos. One by AlphaPhoenix explaining kind of a complex idea of the speed at which electrons go down a wire and how they know what's at the end of the wire, whether there's a actual short where they can travel back to the battery or whether they can't, and all of this kind of stuff, as if there's some sort of decision that the battery makes, and no, none of that I don't think happens. It's hard to say exactly what he's sort of saying, okay, it does work like water in a pipe, but he doesn't use water in a pipe as an example. He uses water in fish tanks as an example, which I don't think is quite the same, but anyway. So I still think it's an incomplete explanation because it doesn't deal with what electrons are. So I guess that's the part I want to explain, is what I think is a better description of what electrons are. Alright, so this Kathy Loves Physics, after, 2 years later, or whatever, 1 year later anyway, she decides to respond to Veritasium's pretty silly video, frankly, where he basically claims that the magnetic portion of what's created when electricity travels through a wire is somehow doing all of the work, okay, and that somehow is conveying electricity to a light bulb or something, and that doesn't really have anything to do with electrons moving through the wire, which yeah, it really does have something to do with. It really is what happens. The stuff inside the wire is doing the work. The stuff that comes out of the wire is just a reflection. It's just the way the universe gets changed because of what changed in the wire. The wire changes, then it reflects different. The universe hits it and it reflects different when it has electricity in it. That's the magnetic portion. Alright, magnetism doesn't come from the magnet. Magnetism comes from the external world being changed by magnets. Okay, so when atoms are polarized, they change what gets reflected off of them. The universe comes in and something different comes out. It's the same amount of stuff, but it comes out in a different way. So I could describe it as purple goes in and blue and red come out. That's a magnet. And that's probably where you have to start, frankly, to understand any of this. But not entirely. Okay. Alright, so I do have a different little drawing board. So it's probably not the time to use it, because who knows how it's going to go. But we'll try it anyway. Alright, so my argument would be is you have to kind of understand electrons as magnetic monopoles. That does work, because that's sort of what they are. Okay, they do create magnetism. Electrons and protons. Charge creates magnetism. When you put two charges together, a positive and a negative, you create a dipole. A dipole is a magnet. Alright. But the key ingredient really is to understand that nucleuses, so if I was to draw a nucleus to an atom, they're net positive. And they're very net positive. Okay, by, the bigger the atom, the more net positive they are, in the sense of, if you added up the neutrons and consider the neutrons an electron plus a proton, then you can understand that they're plus every single electron plus another proton is inside of the, so I mean, it can be a net, as you go up the periodic table, you just keep going higher and higher in terms of how dense the positive of the net charge on the nucleus gets. So metals are pretty dense. That's why they're magnetic. They're pretty heavy. So you can sort of understand that they bind electrons with a lot of pressure. So the real game is that all electrons need the positive protons that are in the nucleus. So even if you have a set arrangement for an atom, the fact is there's other electrons. Okay, the little things here are electrons. The nucleus is there. Other electrons out here and out here are going to be attracted to this positive. They're going to see it. Okay, they're going to see through the electrons and they're going to see empty spots that are going to be a great place to hang out. They don't really count as being part of the atom, but they're essentially what causes an ion, an electron, or two, or three. And basically what's happening when you're creating electricity is you're adding electrons, and the electrons do find a place, okay, where they're attracted to the protons inside the nucleus. They find a place that isn't too repulsive from the other electrons. But the key thing to understand is all the electrons sense each other's condition. They all hate each other. They're all excreting like a negative. This is where the monopole comes in. They're like magnets. So if you have a bunch of magnets, little magnets, and you flip them all to north side, and they all repel each other. So, and you put that in a fixed container, you can kind of figure that if I push another magnet in, all of the magnets will be pressurized. Not just the one, all of them. And if I put two in, then they're all going to be closer to each other, they're going to be pushing on each other even harder. I put three in, they're all going to be pushing on each other even harder. So the argument is basically, you could sort of understand it that although there isn't a closed container, every time there's an electron attracted to a proton, it pushes in towards the proton, and it's only other electrons that keep it from falling into the nucleus. The pressure created by the other electrons. So all of the electrons pressurize even when the electrons are right on the surface. So even if there's a bunch of electrons collecting on the surface, you're getting a high negative charge. All of the electrons are feeling that pressure. And the same is true if I start extracting all these electrons and I'm creating less and less pressure. It's like the pressure, gravitational pressure and mass. The more mass I remove from the surface of the Earth, the less pressure all of the rest of the matter in the Earth is under. I'm taking the pressure off. I'm removing, like I said, if I remove the water from the ocean, the pressure isn't so bad. All right, there's no material above except the atmosphere, and so it's just air pressure, and you don't have this huge crushing pressure. It's the water, the mass, that was creating the pressure. So without the electrons, the pressure inside the material gets less and less. All the electrons start moving further and further apart because they can afford to hate each other. Their hate has more effect, and the more of them there are, their hate isn't strong enough, and they get compressed. So that's voltage. Voltage is the pressure, that is the average distance between two electrons, you could argue. So you could really just make it that simple and just say, what's the average distance between two electrons in a place, a physical place. You can just take your probe and just touch a physical place and find out what the average electron pressure is, and that's the voltage. And obviously everything connected to ground, even through the atmosphere, okay, is going to have its pressure equalized. So yeah, I could touch here and here, and I can go different places, and it's all going to be the same voltage because it's all connected through some conductor. And the key thing is the conductor part, right? Because what's also known is that, if I do this plate thing in space, I have a plus plate and a minus plate, I'm not going to get any flow of electrons. I'm not going to get any flow of electricity. I can't make a spark. I have to have the protons. The protons are they're necessary for the electron to create the pressure. So I need a string of protons which have electrons, and I need a string of nucleuses essentially. And I need to be able to create pressure between electrons so the electrons can push each other. And so basically you need matter to have a conductor. You need the mass of atoms, or you're not going to have any movement unless you heat something enough where you just start breaking all the atoms off themselves and you start shooting whole atoms. So you end up with an electron gun. They call it an electron gun, but it's really shooting atoms. It's breaking atoms. It's not just electrons. It's also other atomic parts. And so it's sort of well misdescribed. All right. So what happens when you connect a battery? All right. So we have a battery. And now we're going to connect a piece of wire. So we connect a piece of wire. What happens to the wire? It just does what it does what the end of the battery was doing. It just says equalize the pressure. So wherever I put the conductor, no matter what I do with it, wherever I do, it's just going to sit there and do the same thing to this wire. It's going to equalize the pressure of all its electrons. So if these electrons in this wire were at, say, 7 pressure, just make up a number, and the battery's at 10, well, then the battery is going to put these at 10 pressure. And that's all. It's going to happen. It's just going to equalize. And so whatever, so the positive, as soon as I connect a positive, then I'm going to be doing the same thing, and let's do the negative. It's just going to go right through the wire near the speed of light, a little bit less maybe, and the pressure is going to equalize, because what I'm doing is I'm either shoving an electron in, which makes all the other electrons push into each other closer, so the average distance between an electron gets smaller, or I'm pulling electrons out, and I'm getting the average distance bigger, because there aren't as many electrons in the space. They're not as crowded, so they can be further apart. And so that's all I'm doing, is moving electrons close, moving electrons away. And obviously the more I'm, if I actually connect this circuit, okay, through a conductor, well, then the side that's pushing electrons, all right, can push the maximum number depending on how many can get through the conductor. So however, a little tiny wire, it's going to be more resistance, less volume. Big wire, then I can get a higher volume of change through the wire. But there's really no reflection in any real sense, in the sense that obviously it takes, as the electron pressure is changing, it keeps moving electrons in. And obviously there's a point where all of those electrons don't terminate. That is, they don't find an ending. So they want to keep moving. The pressure wants to keep moving. So the pressure, let's just imagine, it starts, okay, and it just keeps going because there's nothing to stop it. There's no friction. There's nothing eating the energy. The energy is forever energy. So if you can think of it sort of like heat. And there's a complete vacuum around the heat, so there's nowhere for the heat to go. The heat has to stay in the conductor. So yeah, it starts to fill all the little spots as it's pulling, but it's not getting used per se. It's not ending. And so yeah, when there's a certain point where it satisfies it finally gets to the ultimate pressure of 10, and then there's still all this back pressure because these are still in the wire, and it's already equalized the pressure to 10, so now it has more pressure than it can deal with in the sense, and so then the voltage goes up because the pressure goes up because of, it's like a lag time. So in the sense, water does that, in the sense that there's a lag time. You get the water moving and it has momentum. It can't, all of the water can't go somewhere. You could argue, let's see, what's the right way to say that? All of it's not good. It's like a musical chairs. There's not enough chairs for all the electrons. So eventually half the electrons that went down the wire aren't going to find a chair. So those are the ones that create the back pressure that increases the voltage temporarily. And so, and puts a little bit of back pressure on the battery. But it's, milliseconds, tiny bit of time it takes to equalize, but you're just equalizing pressure, all right, and there's really, it's that simple. So in the one circuit, in the AlphaPhoenix video, he's talking about a fork in the road, so you have a positive and a negative, and yeah, I think he uses a twisted pair. So he twists them and then has them fork into a place where there is a short, and then has them twist in this direction where there's an open circuit. And the fact is yeah, all this is just conductor as far as the battery can see. So the battery is just saying, as long as the pressure keeps reducing, that is, it throws an electron in, that electron keeps moving, the pressure keeps moving, then electrons will keep going in because the pressure will keep getting low. You have a 7 here and you have a 10 here. The 10 hits the 7, both of them talk to each other essentially, and what do you end up with? You end up with an 8.5, the average. And then the 8.5 is next to a 7, and then that reduces to a 8.25 or whatever it is. It just keeps doing that. The pressure just keeps moving until there's no place for it to go. All right, so there's no more electrons to push closer to each other. You can't pressurize any more of the electrons because you're already at the 7 or whatever the number that the battery started with. You've achieved that number. All right, and that's what both sides do, because they don't know this is a place where they can go all the way back again, and they don't know this is an open circuit. So to start with, they just shoot down the pipe. Now the truth is if you have a switch where you're only switching one side of the circuit, then obviously the other side of the circuit's already has the advantage where it's already very plus. So that you'd have two sides here where the plus side could be already connected to the battery. It's already charged to whatever, 7 or 8 or 10 or 15 or 100 volts. It already has the voltage, and now it's just waiting, okay, for you to throw the switch, okay, to let the other side charge up. But it's all just capacitance. I mean, the wire is just a capacitor, and you're just basically filling the capacitor, and it's a very weak, small capacitor, and that's, but that's all it is. It just takes a little bit of time to charge the wires. You could argue it's that simple. You're just charging the wires, and if the wires have a short, well, then it's going to just keep pumping electrons in one side because the pressure is going to keep reducing in front of it. The pressure is always going to be less in front of these electrons, and so this side of the battery is going to still have electrons to pull. You're going to keep increasing the pressure here in front of this side, and it's going to keep pulling, and this side will just keep pushing because it's going to keep having a low pressure in front of it. And the differential will go from 7 to 6 over here, and at the end of the at the end of the wires, the end of the battery, you'll have the highest potential. But yeah, the further out you go in the wire, the potential gets lower and lower in terms of the difference from this side to this side might only be 3 volts. But anyway, that's sort of a not as important technical detail. All right, let's see what else I could say, how else I could say it. All right, to make the point that it's just electrons moving. I guess what I really should get to is the whole EMF, all the stuff that is inductive. Okay, it's just a byproduct of when you're putting electricity in a wire. Now, if I if I have a very high pressure, then the high pressure can travel just through a few atoms and go right through the conductor. But if I want a lot of wattage, okay, and I have a low voltage, I'm going to involve a lot more atoms in transferring the pressure. So I can have a low pressure but a high volume of electrons. So if it's a high volume of electrons that can go through the wire at a low voltage, then I'm going to change lots of atoms. Lots of atoms are going to get polarized by the process of the electricity moving. So you can move the electricity, the pressure, through just a few atoms, and that's kind of what happens with lightning. You're just involving a very few atoms of the atmosphere in the transfer of the electron pressure. So all the electron pressure, the differential in the pressure between the clouds and the earth, is all solved by one little solution, one little pathway. And the same thing can happen inside the conductor. Inside the conductor at high voltage, you just have one little pathway. Very few atoms are affected. They don't even know the pressure change took place, let me put it that way, because it happened so quickly and it just went through a very few atoms. There just didn't need as many. So you can have 10,000 volts and you'll affect 3 atoms. I'm exaggerating, you know, and then you can have 10 volts and affect 10 million atoms, and that would be the high amperage. So high amperage basically means more volume of electrons, so it's more particular. There's let's see how to say that. The pressure is lower, that is the velocity of the electrons, so you're letting more electrons loose. So I guess it's sort of like figuring how you open the gate, and you can let just, you have a high pressure, but you open the gate and only one electron at a time can get out, or you open the gate and a whole bunch of a big volume can come out at once, but it comes out at a lower pressure. So it's sort of like water coming through a hose, in that sense that if you make it so only a few electrons can take the path, they're going to be at a very high pressure. But if a lot of electrons can take the path, then it's going to be a very low pressure, but it's a high volume of them. And so you can have two circuits with the same wattage, that is the high voltage at low amps or the low voltage at high amps. And the key is how many atoms will be involved in the transfer. So that's why there's magnetism induced in wires by low voltages at high amperages. It's because every time you shove an electron in and change the electron configuration of the atom, that is, the atom has a configuration, you're adding pressure, which pushes on these electrons, crams them closer together or further apart. You're basically changing the profile of the atom, that is, you're polarizing it, you're shaping it. So you could argue that every time electricity is going through a conductor, it's compressing atoms one way, and that's making them bipolar. It's polarizing them, and it polarizes them in the perpendicular to the flow of the electricity, and that's why you end up with magnetism. The magnetism isn't a field being excreted by the wire, it's just that the wire has turned into a bunch of polarized atoms, and it's mimicking a magnet, in the sense that the external world is going to bounce off of its surface different. So where purple went in and purple came out before, when you put electricity in, purple goes in and red comes out this side and blue comes out that side, that kind of thing. All right, so I might take a pause and see if there's anything else. All right, so in closing, I guess I'd say that the thing to understand is that there's really nothing that happens inside of wires that's called an electric field. There's just the magnetic field. So if you can polarize the atoms inside, make them plus and minus, and have them all point in the same direction, you can create a magnetic field, that travels between substances, and it travels between them in the same way that light reflects off of us. I mean, I can have light reflect off of a surface, and I can see it a mile away. Well, yeah, the signal of the magnetism is just as real as a light signal. The magnetism's moving the speed of light. The signal is as real as a lighthouse signal. And depending on how much wattage I put through the wire, I put megawatts, I can create a radio signal that isn't an electrical signal, it's a magnetic signal, and I can make it visible, 50 miles away, because it's a very bright signal. A lot of photons are coming in, again, purple, and coming out, plus and minus and north south configuration. It's just a pattern of north and, like a bullseye, you could argue, red, blue, red, blue, red, blue. It's a signal, a pattern, and that pattern can be seen by other dipoles, and they will recognize it. They'll be hit by it, and they'll be moved by it, and when they're moved by it, they're going to create the same thing that caused them, which is electricity. So when you hit the atoms with the magnetism, they turn, they polarize, and essentially duplicate the very process that pressurized the pressure that caused it in the first place. And so we see photons because we turn them into electricity. We don't see the photons, we see electricity. And we see the electricity because basically the photons had a pattern that could cause the same effect in an atom to make electricity. So some photons will hit and do, some elements or bits of energy can hit, and they aren't in a pattern. They're not in a pattern, they can't duplicate electricity. But if they are in a pattern, they can. So it's just like the domains inside of a piece of iron. If they're random, then there's no magnetism. Even though there's a bunch of magnets in the magnetism, in the iron, the little magnets can't do anything because they're not all pointing in the same direction. So you know that anything you do to orient them in the same direction makes them turn into a magnet. It's not like they didn't exist. It's not like the magnetism doesn't exist. It's not like they're not reflecting energy from the universe. It's just that it's not in the right pattern. So lots of energy hits, just like a photon, but not all of it reflects as a photon. And the same is true for magnetism. Only magnets can see the pattern. Something that's not polarized can't see the polarized pattern. Probably a way to say it. But anyway, the magnetic effect is just because you've changed how the conductor looks. It looks different to the outside world. So you're not excreting extra energy from the wire. The wire is not excreting any extra energy. It's just reflecting the existing universe differently. Same amount of energy, it's just in a pattern, and patterns matter. So there's no waves, it's just all little particles banging into stuff, and depending on whether the thing they're banging into is turned this way or this way, they're going to reflect different. Something's coming this way, it's going to reflect different if it's pointed this way than if it's pointed this way. That kind of thing. It's pretty much that basic. Alright, so I think I'll call that a video. And, go on and on. It's kind of a deep subject. But we'll say that's enough for now. So anyway, till the next time and such, and so forth, and whatnot. This camera's not right. Yeah, not right at all. Anyway, till the next time and such. Just won't stay. All these little technical issues. Try that. Nope, still won't stay. Now I turned the other way, the other camera doesn't work. But I'm not using the other camera right now, so that wouldn't matter. Alright, anyway. Just never mind the last 35 seconds. So, till the next time and such.